Okay, so a light spring of natural length 1.2 meters and modulus of elasticity 4.3 newtons is placed on a smooth horizontal table. One end is fixed to a point A, the other end is attached to a particle P of mass 0.1 kilograms, which is initially held at rest at a point B on the table, where AB equals 1.7 meters, and at time t equals 0, P is released. Okay, so I've mocked up a clear diagram here of the dimensions, so to speak, not to scale, but we've got here this distance here representing the natural length. Okay, so that'll be L of the spring, which is 1.2, and it's stretched, isn't it? So it goes from A to B, which is a distance of 1.7 meters. So you can see it's been stretched there initially 0.5 meters, okay, because that will add up to 1.7, yeah? So we've got the strength of the spring being 4.32, so the modulus of elasticity, okay, and we've got everything in place then. This is where the center of oscillation is going to be, okay, where the spring would be at its natural length. That's where it wants to be, isn't it? The spring at its natural length, that's where it wants to go towards, okay. Now, it says initially it's held at B, okay, right, and then released. In part A, it says show that the motion of P is simple harmonic and state its period, center, and amplitude. Now, to show that it's simple harmonic, it's no good considering it at P initially, because at P it's held at rest and it's not performing SHM, it's just been held there, okay? So we need to consider it as it's in motion, and the best place to consider it when it's here, okay? So we'll say, for A, consider particle moving, okay, in direction of increasing x, okay. Now, of course, increasing x, we think of x being measured then, the displacement from the mean position, okay, so we consider it as it's performing SHM, okay, it's performing SHM there, and we're looking at it when it's there on the move, okay, it's there. So we want to show that actually, mathematically speaking, it is actually doing SHM, okay. So to do that, we'll apply Newton's second law, and we need to then consider the forces, right? So when it comes to the forces, think about the forces acting on P. At that point there, of course, the spring has been stretched beyond its natural length, okay. So now we've got tension pulling it back. So the only force acting on P is the tension there. Now, when we apply the Newton's second law, it's in the direction of increasing x. So the t will be negative x, supposing that. So we have minus t, okay, equals to mass then, which is 0.1 kilograms, so 0.1, and then acceleration is x double dot. Okay, so we've got that. We haven't shown it's performing SHM yet, because it's got to be of a certain form for that. So what I'm going to do, I'm just going to label that for a minute. You're going to label it 1 or star or whatever. We'll come back to it. What we can do is use Hooke's law. Okay, using Hooke's law. And we can use that because we know with Hooke's law, a formula, okay, and we know the modulus of elasticity lambda is 4.32, okay, and we know the natural length is 1.2. So sub those values in, and that comes out rather nicely to be 3.6 when you divide them, x. So if we sub that back into star now, we get minus 3.6x, because minus t, yeah, so t goes in there, equals to 0.1 x double dot. Divide then by 0.1, so then we get, if we divide through by 0.1, you get 30, or minus 36x is x double dot. Or in other words, x double dot is equal to minus 36x, and that is SHM, okay? It implies SHM. So we can say literally motion is SHM. We've proved it mathematically because it's of the form of SHM, which is x double dot is equal to minus omega squared x. Okay, it's exactly that form there. Now, from that, straight away, we can tell what omega is going to be, because omega squared's got to be that. So omega squared is 36, which implies omega is the square root of that, which is 6. Okay, so we've got omega. We've shown this SHM, and we've got omega. Next then, we've got a status period. So the time period, of course, then we'll be using t is equal to 2 pi over omega. And because we know omega is 6, we get then pi over 3 seconds. Okay, so we've got that. The next thing then, it says find the center of oscillation, center and amplitude. So the center is going to be here. If we go back to the diagram, the center, okay, as it asks for in the question here, the center is always where the spring is at its natural length, okay, where it will revert back to. It'll want to go there, it'll want to go back to its natural length. So you literally, how do we state that? We could say the center of oscillation is 1.2 meters from A. So we can say that. So the center of oscillation is 1.2 meters from A, where the spring is at its natural length. Okay, and then finally then the amplitude. Well, the amplitude is easy because you just look at what the initial stretch was to be. Because you stretched it to 0.5, that will be the amplitude. So it'll spring back, and it'll spring back that way. I've marked that out there. That's 0.5 as well. So 0.5 back to 0.5. So the amplitude is based on the initial stretch. So the initial extension, so the amplitude is 0.5 meters.